Hey Calculus, we are going to learn how to do related rates problems. Related rates problems have to do with things that are changing with time. Okay, so they are rates of change, which are derivatives. All right, so the first thing you're going to do is you're just going to draw a picture. So for this first example, air is being pumped into a balloon, a spherical balloon. All right, so you just need a picture. All right, so the first step is just to draw the picture. So we have a spherical balloon. All right, and there's a little string for our balloon. Okay, now our volume is increasing at a rate of 10 inches cubed per second. Be on the lookout for numbers that have units that are a rate. That is a rate. Okay, that is a fraction. It is inches cubed per second. That is a unit for a derivative. All right, so just be on the lookout for that. That is a rate. Okay, now it's asking you for how fast. All right, again, fast, that's asking you for a rate. All right, so that's something to be on the lookout at the end. Your answer will be a rate of change. All right, so how fast is the radius of the balloon increasing when the diameter is 8 inches? All right, so the diameter, goes from one end to the other. So my diameter is equal to 8. All right, so that is our first step. Draw a diagram. The second step, we're going to organize all of our information. And we're going to order it into 3 columns. What is given to us, all right, anything that we can find on our own, and then the unknown. All right, what is the question asking us for? All right, so we're given right off the bat, the only thing that we're actually given is, well, we're given the diameter is 8, and we're also given the rate, the volume. All right, so the volume increases at a rate of 10. So that is a rate of change. Anything that's changing has to be assigned a rate variable. All right, so we could call it V prime. In this unit, we're going to use Leibniz notation. So we're going to give that dv dt. All right, that is the same as V prime. All right, it's the derivative of the velocity. All right, so again, this is not a fraction. It is a symbol for the derivative of the velocity, and that is 10. Okay, now let's try to figure out what our question is asking us for. How fast is the radius of the balloon increasing? All right, so again, those are key words that it's asking us for a derivative. The first key word, of course, is how fast, and then increasing. All right, so the radius, how fast is the radius of the balloon increasing? It's not asking us for the length of the radius. It's asking us how fast the radius is changing, the rate of change of the radius. All right, so we're looking for r prime, but we're going to use Leibniz notation, dr dt. All right, the rate of change of radius. All right, that is what the question is asking us for. Again, that's the same as r prime, but we're going to use Leibniz notation. All right, now, the third step is what equation can we find? You have to find an equation that matches the problem. All right, this is the volume of a sphere. All right, we're dealing with the volume of a sphere. So now you have to go back to geometry and you have to get that formula. The formula for the volume of a sphere is V is equal to 4/3 pi r cubed. Remember, volume is always cubic units. All right, so that's our third step. Find an equation. All right, now let's look at the variables in our equation. We have a V and we have an R. So we need the radius. We don't have the radius, but we have the diameter. So we can find the radius. The radius is half of the diameter. The radius is 4. All right, so that's kind of your first 2 steps. Make a quick sketch, organize all your information, and find an equation. Now, every variable in your equation also has to have a rate variable. So we have volume, and we have the rate of change of volume, dv dt. We have the radius, and we have the rate of change of radius, dr dt. Every single variable needs a length variable and a rate variable. V dv dt, r dr dt. All right, the fourth step is we are going to take the derivative of this. All right, when you take the derivative in related rates problems, you have to use the chain rule on every single variable. We have to use the chain rule on V, and we have to use the chain rule on R. Now, let's go back to implicit differentiation, just to review. All right, do you guys remember when we took the derivative of y to the first? Okay, the derivative of the outside function was 1 times something to the 0. The inner as is was y, and the derivative of the inner was y prime. When we simplified that, the 1 comes down. Anything to the 0 power is 1, so 1 times y prime. If you remember, the derivative of y to the first was y prime. All right, so we can apply that to this. Okay, what is the derivative of v using the chain rule? Well, that just changes to v prime. All right, so again, step 4 is take the derivative. Every single variable you have to use the chain rule. It's kind of like implicit differentiation. Okay, now moving right along, 4/3 pi is just a constant. So that comes along for the ride, 4/3 pi. And now we have to use the chain rule on r cubed. And just like implicit differentiation, it's 3r squared, and we use dr dt instead of r prime. We're going to use Leibniz notation. So there's my derivative. All right, the fifth step, now we just plug everything in. All right, v prime, now again, we're going to use Leibniz notation. So we're going to change this. V prime is the same, of course, as dv dt. All right? So we have dv dt here. This dv dt represents the rate of change of volume. And we have that right here. So we're going to plug in 10 right there. 10. 4/3 pi, of course, just comes down. The 3 comes down. We know that the radius is 4. I can plug that in for the radius. And dr dt. Once you plug everything in, you should only have one variable left, and our variable is dr dt. That's what we're trying to find. All right, so now we just solve for dr dt. Okay, one thing that we can notice is we can make this 3 right here a fraction, and that helps us because these 3's, of course, will cancel out. So then we have 10 is equal to 4 pi. And then if we square the 4 here, we get 16 times dr dt. All right, now the 10 can come down. I can go to my calculator and get 4 times pi times 16. That gives me 201.06. And then our variable dr dt comes down. To get dr dt by itself, we just divide both sides by 201.06. 201.06. Those cancel out. Dr dt, our rate of change of the radius, is 10 divided by 201.06, which is very, very small. I'm getting 0.05. Now you also need units. This is a rate of change. So you need a rate of change unit, which is a fraction. All right, so if we go back up to the original problem, I am dealing with inches, and I am dealing with, this is going to be seconds right here, seconds. All right, so, and the radius is just a length, so it is just inches per second. Okay, we know that the rate of change of volume, dv dt, was inches cubed per second, because volume is cubic units. If we had a rate of change of area, dA dt, rate of change of area, or A prime, that would be inches squared per second because area is square units, and we know that a radius is just a length, so it is just inches to the first, inches per second. Okay, that is example number 1. Go to the next video for example number 2. Related rates is tricky. It's kind of messy and hard, but just hang in there. You'll get it. Stay positive.